So, before Markov chain, everything is okay.
Yeah, everything, I guess, until the decision making, it was
Game
less
theory, no
deep.
problem. Game
Oh
theory, no
yeah, and also
problem.
also the game theory.
Queuing also no problem, right?
Yeah, that's basically like a system, right?
Yeah,
So
just a system with queuing, right? So there is no problem with that. So only the Markov chain is hard for you.
yeah, and also like the Marx entropy.
Max entropy.
Yeah.
Why max entropy is hard?
Uh, I don't really get it. Like
Okay, so maybe I should explain briefly. Yeah? So maximum entropy is a technique to optimize things
mhm.
where you have a missing data.
Oh, to handle the missing data.
Yes, if you have missing data, then you assume maximum entropy to
Mm-hmm.
fill up those data,
Mm-hmm. Oh,
right?
yeah.
I mean, to compute maximum entropy, you can do, right? Just solver, right? Isn't it?
Yeah, yeah. But if you don't understand like the concept, you don't know like what should be put, what should like interpret the result.
Okay, so the most important part in maximum entropy is to compute probability because entropy comes from probability. Okay,
Mm-hmm.
how are you going to compute probability depends on the invariant. Okay, that's the start of point that you start confused. What is invariant,
Yeah.
right? Invariant is something that don't change.
Mm.
Okay, something that don't change or something that actually uniform probability distribution.
Mm-hmm.
So in my example, I applied queuing theory for, no, I applied maximum entropy for queuing theory. Is that correct?
Yes. Mm-hmm.
And I give you example that, look, if you multiply the demand and supply,
Mm-hmm.
okay, and you assume that is the one that you want as
Yeah.
equal, right? So the equal of demand and supply, multiplication of demand and supply, n times r, right? The one that you keep in the slide. So then that will become the probability that you want to get. Based on that, you can compute the maximum entropy. In queuing, what is the invariant? The invariant is probably the total cost, right? What is the total cost? The waiting time and the service,
Surface time.
the service cost, yeah, not the time. The waiting cost and the service cost,
Um.
right? And then you sum all of that, become total cost. That is the one you assume as invariance.
Oh, okay.
Okay, so something that you want to do as invariance, that is the one that you compute as probability.
Okay.
Okay, I hope that is clear. Joy, say, Livy was asking about maximum entropy. So, is it clear for you, the maximum entropy?
Wait, I gotta check because I forgot. I need to review. Oh, wait, sir. Maximum entropy. Do you have an example on which one? Because I keep on getting mixed up between operation research and differential equation.
Okay, so maximum entropy is an optimization technique, okay, to fill up the missing data. I give you several slots of numbers, and then there are some empty slots, and then you need to fill up those missing slots. That's the beginning of entropy, right? So using this maximum entropy, you can fill up any data. Okay. In fact, this is what I'm doing in IFN. So let's enter the IFN choice here already. Okay. So now IFN, okay, if you look at this IFN, this is how I compute the probability in IFN, right? How? This value, yeah, I got the node entropy here, okay. So I got the node entropy here. That means every node you can compute the entropy and then sum for all nodes, right? So node I, and then I have some proportion of the flow in that node compared to the total flow in the network. See, that will become my network entropy. So basically the network entropy is the multiplication, okay, between the probability of each node compared to the with the node entropy itself. Okay. So you will ask me, how do I get this? Okay, so that's again trial error, right? So, but at the same time, the meaning, yeah, you get the meaning of that. Okay, so once you get this, you can start to get the maximum entropy. Yeah? This is basically maximum entropy, and then what do we want? This is stochastic constraint, and this is pre-magic constraint. This is the total flow is given. So the purpose is to compute the node value Vi. Okay, so I also give you the software, right? The Excel add-ins. Did you try already? In Lentera, there is Excel add-ins of IFN, so that you don't need to compute all of this. Okay, it's already in the software that I make, so that you can directly use, okay, without computing this.
Oh yes, the Excel add-ins, right?
Correct. So now I want you to learn. Okay, let's do it in whiteboard. Can you see my whiteboard? Okay, so I want you to make on your own. Say, for example, here I have, how many nodes you want? Say, this node and then this node. Say 4 nodes, is it okay? Or you want to five nodes? And let's make any network that we can make. Okay. Say one more here so that you can see 5 nodes. And I want to make a network that is irreducible. That means, say, I call this A, I call this B, I call this C, D, and E. Okay, so that from any node I can go to any other node. Okay, and then I can fill up any. Oh, so I go here. Okay. Now, from any network that you can create, okay, now try to assign any probability that you want. For example, from A here in this example, from A can go to B and can go to D, correct? So say I want to say, look, to go to B is 1/3, okay, and to go to D is 2/3. Okay, so the total probability out is 1. The same thing here, say from B, I can go to C, I can go to D, right? Then you can say, okay, I have a probability of half and half. Okay, from C can go to A and can go to D, right? So you assign probability, what probability you want? Say you have a probability of 1/5, and this is 4/5, 4/5. D to E, there is only one link out, so that's probability of 1. The same thing from E to A, also have only one link, so in that case, the probability is also 1. Now, given this network, can you compute the flow? Can you compute the flow? Is it possible to compute the flow based on this network? How are you going to do? Right. So can you see the problem at hand? Okay. You have a system. See, the network represents the system, right? And then in that system, everything that out of every node, you know the probability. At this moment, if you want to apply, okay, say this is a road network as an example, right? And then you said, how I will get that probability, right? Oh, probability can come from anything, right? Right? So in that case, what is the simplest thing that you can get probability out of the road network? You don't know the flow, you want to know the flow, right? So what is the simplest thing that you can think of to get 1/3, 2/3? What is that? How do you get that? The simplest thing is probably the number of lanes, isn't it? Right? Or the width of the road. Right? So if I know the width of the road out of this intersection, so the node here represents the intersection, right? So out of this intersection, okay, so say this is 3 lanes, so in that case, this is 6 lane. No. Oh, this is one lane and this is 2 lanes, so the total is 3 lanes, right? That's mean 1/3, this is 2/3, is that correct? From A, B, only 1 lane. From A to D, 2 lanes. Then you get the probability to go to from A to B is 1/3. Because the total of A, B, and AD is 3 lanes. Correct? Can you imagine that? Okay. If this is difficult, let's do it easier. Okay, let's do it easier. So let's assume they are all equal probability. Okay, let's make it simple so that because I will make it simple so that you can compute easily. So this is one. So 1/2, 1/2, right? Everything go out is 1/2, 1 half, so that you can compute easily. So if I have 100 here, okay, from E to A is 100 flow, say 100 vehicles per hour. How many will go from A to B? Because probability 1 half, so you get 50, correct? Okay, so here we get 50, here we get 50. Okay, so I will remove the 1 half so that you will know. Anyway, you know already this is 1 half. So this is 50 going from A to B, right? Because probability is 1 half, so how much is B to C? Can you get? Leafy going in to this node B, how many flow going to the node B?
Only one.
No, I mean flow.
Oh, the flow.
Going in. Remember, I assume this is 100, and then because probability is high,
Oh, 150.
this is 50 here and 50 there, right? So now going in to node
50.
B. Now let's focus in node B. How many going in?
50.
Correct, 50, right? Now divided by half,
25.
correct. So this one is 25, this one is also 25. Okay.
Mhm.
Now going to node, how many?
To node C,
This one, right?
yeah, 25.
So in C have 25. Now you get half, right?
7, yeah,
So how much is this?
17,5.
12.5, correct?
Yeah, 5.5.
Become 12.5. Here also 12.5, correct? Okay. Here a while ago we already computed this is 25, right? Okay. So then, and this is already 50, right? So then how many going to D?
37, 87.5.
Very good. So 87.5, right?
Mhm.
And then in that case, how many is the flow from D to E?
87.5.
Excellent. So this is 87, okay, 0.5. So something is wrong.
Mm.
87.5, but out is 100, so something is wrong.
Oh, this, I guess from the C to A, we haven't counted.
Yes, so this must be,
The A to D must be,
this one must be 87.5 plus 12.5 now become 100. So, and then you divide
yeah,
by 2, is that correct?
yeah,
Right. So now is it correct for all nodes? They are balanced?
yes.
Yes. Okay. Now, can you put this into matrix now? Because you're already having balance. Can you put this into matrix? So now, can you draw a matrix? Yeah. This is A, B, C, D, E. Yeah. And then you have A, B, yeah, C, D, E. Yeah. Can you make it? So, and then put into matrix, what is the flow? Yeah. So from A to B, how much? 50, right?
Yeah, 15.
And then what else? From A to D, yeah, again another 50, yeah. And then from B
B to
to
C,
C, 25.
25.
And then B to D, 25, right? And
Yes.
C to
C to A, C to A
12.5,
12
and then C to D
G.
12.5. Yeah? Correct? And then D go to E.
E.
Yeah? D go to E 87.5,
5.
right?
Mm-hmm.
And then from E go to
A.
A, how much?
57.5.
7.5. Okay. Okay. Very good. Now you get this flow matrix. Okay. Can you sum to the row and sum to the columns?
Mm-hmm.
Can you sum? So
Yeah.
here 100, right?
Yes.
This is
50.
25. This is 87.5.
57.5.
87.5. Eh? 87.5. Is that
Mm-hmm.
And then here you get 100, 50, 25,
25.
87.5, and then 87.5. You see the sum of row is exactly the same as the sum of column. So this is pretty magic.
Mm.
The next question is it always like that? Yes. Okay, so my theorem said it is always like that. Why? Simple. Because they are balanced. In each node, they are balanced.
Mm.
Correct? And
Yeah.
that I said as VI. Okay? VI, yeah? Or VJ here. Right? So each of these, so V1, this is the node value. Right? If you look at this, the node value represent how much in A, the total flow in, yeah, or the total flow out. Okay? In A is 100. Yeah? In B is 50. Is that correct? Right? In C is 25. Okay? In D is 87.5, and then in E is again the same 87.5. So as long as your network is irreducible, I mean strongly connected, from any node you can go to any other node, okay, this characteristic exists. This is what is called IFN, yeah? Ideal flow network. So up to here, is it clear or not? Definition and how you get it manually.
Yeah, it's clear.
Clear, yeah? So if you want to do it in Excel, okay, so you can just open. Say I will stop the sharing. How to do it? So let me show you the Excel. Right. So in Excel, you need to go to options and then Excel add-ins. And then you already installed the ideal flow. So you click the ideal flow and click OK. Yeah. If you have it, when you right click here, you will have a menu of ideal flow. Or in the add-ins, you also have the menu of ideal flow. My question, do you have it? The one in Lentera. So the one in Lentera, you're supposed to get like this. Okay, inside that file, you're supposed to get the example and then the ideal flow Excel add-ins, and then the documentation, right, in the zip file. So if you double click this ideal flow Excel add-ins, okay, it will copy this into this folder automatically. So this one, okay. Of course, your folder name is based on your name, but usually will have a name of AppData Roaming Microsoft Add-ins. Okay, and based on this, now you can go to the file option add-ins. Is it working in your computer?
Yes, it's working. I have already.
How about you, Joy?
Oh, wait, sir. So when I click
Double click.
when I double click the ideal flow,
It will automatically go install to this.
it opened in WPS.
Oh, what is WPS?
WPS Office, like a PDF
Ah,
reader.
because you are using OpenOffice.
I don't know.
Okay, if not, you can just go to your this kind of folder. Can you go to this folder and then you copy that ideal flow into this folder?
Copy ideal flow to
This
Microsoft Add-ins.
yeah. Of course, the user and then your username. I don't know what is your username. Okay, and then the app data roaming. This is actually hidden folder. So you need to check this hidden item so that you can see. Is it working? Once you have it, so you can go to the file options, Excel add-ins. So now, once you have that, so you can create a new blank book. Okay. So, and then you can create equal and underscore. Right. For example, let's create what is called capacity matrix. So I will put random, okay, random capacity here. Or you can create also random stochastic matrix. Okay, but let's name it random capacity. So I just close this. And then any size that you want, you can just create. Yeah? Any size. For example, I make 5, right? 1, 2, 3. So 5 by 5. So once you highlight this, so you press Shift, Control, Enter together. Oh, sorry, F2, Shift, Control, Enter. Together. So this is like the number of lanes. Yeah. So this is like A, B, C, D, E. And of course, this is random, so you can just put A, B, C, D, E. Right? So this is the number of lanes, yeah, from one node to the next. And if you take the sum, of course, okay, they are not pre-magic. Yeah? So if you take the sum, they are not pre-magic. So I put the sum here also. They are not pre-magic, yeah. So you can see this is 3 and this is 9, not the same, right? So this is, I call this capacity matrix. Yeah. So capacity matrix means the lane capacity. Okay. And then from here, the next step is easy. You can calculate the stochastic matrix. What is the stochastic matrix? This is the transition of Markov. Stochastic. The Markov transition matrix. How to compute? Easy, yeah. So you just get the value of this, right, divided by the sum in each row. Yeah, this is the sum of each row, like this, right? So, and then you take dollar sign, okay, and you copy it all. Yeah. So, of course, the sum of each row will be 1, right? Because this is stochastic matrix. By definition, the sum of each row will be 1. Right? So this is the sum. Okay. This is the sum. Okay. So of course, you don't want that. You can also use n underscore, yeah, capacity to stochastic is the same thing. Yeah? You will get exactly the same thing. Okay. And capacity to stochastic, that's exactly the same computation. Yeah, each cell divided by the row. Okay, so I can calculate that. Okay, and then F2 shift control enter. I get that. The same thing. Yeah, the sum is still 1. Right? Is this clear or not? So from the stochastic matrix, now you can calculate the ideal flow. Yeah? Ideal flow. Okay. The ideal flow. Okay. And now I copy this. The computation, either you use matrix formula like Markov chain, or you can use maximum entropy with the one that I presented in the slide a while ago. Okay, so using this software, you don't need to compute, you just need to put the function, right, where you want to put. From stochastic or from capacity matrix, is up to you. Okay, so I will put capacity to ideal flow, right? So in that case, I will put this. This is the capacity. Okay, so I close this, and there I just put F2 shift control. Okay, now if you calculate the sum of columns and rows, it must be Premagic. Yeah? It must be Premagic. Let us see if it is true Premagic. Oh, exactly. Yeah, you can see this is exactly Premagic. So I will put different color here so that you can see. Okay, see 128. This is 128. This is 158, 158, and so on. Right? So exactly Premagic. Again, if I press different F9, I will get random value of random network. Right? All create the same. Yeah, which is this is the sum. So you can get the ideal flow out of either the stochastic or from the capacity matrix. Okay, if you don't want this to be random, so you can fill up, say in your exam, you can fill up this one on your own, right? Or or you can fill up this stochastic on your own. Up to here, is it clear or not? So once it is clear how to compute, okay, let's go to the application and the properties. Is it okay? So make sure that you are okay with the computation. Livy, Joy, tell me. Again, the meaning first. Do you understand the meaning of capacity? Imagine this is a road network. Okay, imagine this is not road network. This is the number of lanes. Okay, so 9 here represent from A to C, 9 lane. Okay, so from B to A is 10 lane. Wow, a lot of lanes in one road. Okay, right. So from C to A now 4 lanes. Okay, from C to D in this case 6 lanes. And so okay, so and how about stochastic? What is the stochastic? This is the transition probability, yeah, which is from this capacity divided by the sum of each row. 9 divided by 9 is 1, right? So here you have 4, 6, and 6. So in that case, 4 divided by 16, so 0.25, right? And then 6 divided by 16, 0.375. Yeah, the same thing here. Is it clear? So that row D here, 3 and 3, so the sum is 6. So in that case, 0.5, 0.5, right? Stochastic is the probability going out of the node. This is the Markov chain is about. The stochastic matrix is the Markov chain probability. Is it clear?
Yes.
Yes. And then from there, okay, you calculate. Okay. If you want to calculate manually, you can. You can calculate using computer, so it's already computed here, right? Because if you compute manually, this is quite long. So you have a software to compute so that you see, so that balance, right? See, the sum of row is exactly the same as the sum of column. So ideal flow meaning is pre-magic and irreducible. Of course, the irreducible come from the stochastic and the capacity. Okay. So the computation here is just to make it balance. And you see the ideal flow is practically always integer. Yeah. You can press F9. Yeah. This is not integer. Actually, this can be converted to integer, but the integer is very big number. So that's why we put it into this basis ideal flow. Yeah. So that not too big. If the integer is rather small, I will put it into this number. Yeah. Clear? Can you make it, Joy, Devi?
Yes.
Joy, you have still have problem?
Uh, Am I lagging? Oh, I wasn't able to add in the add-ins, so I need to find out later after class.
Okay.
But so far, I'm following through with your Excel explanation.
Okay. Okay. So good. So in that case, let's go ahead with the application. Right. So I come back here to the slide. So the computation is fine. Okay. So again, the most important properties is must be reducible and pre-matching, right? So if you have weakly connected, okay, or you have external environment that you want to model, then you can optionally add cloud. Don't forget, the ideal flow is actually relative flow. Okay, then we can actually produce what is called equivalent IFN. Okay, I will explain in a moment. Okay, what is equivalent IFN? Yeah? We already discussed this last meeting. Okay, so you can add the cloud node here. I think you have practiced this last meeting, right? So, and then you can get strongly connected. Yeah? If you are weakly connected, okay, you add one cloud node, you can make it strongly connected. Okay, and this is an example, right? If you have this intersection, okay, and if you look at the flow, see, we are not even start from the capacity, we start from the flow, okay. You have one A, B, C, D, E, right? This is the node name. We don't need to know the how they move, yeah, from one to the others. Okay? And then if you add the cloud node here, Z, okay, and suddenly everything will become pre-matching. Yeah? So the same thing with this T intersection. It of course this is not pre-matching, so the sum is 1000. This is 150. But once you include the cloud node, okay, the sum suddenly will become, okay, pre-matching. You see, 1150 also, 2100, 2100, and so on, right? So this is another example of what is called waving section. So this is in the roundabout or in the U-turn. Usually we have this kind of system. Again, you can make it pre-matching simply by adding Z. Yeah? So this is all the same. When you add Z, which is the cloud node, everything now becomes pre-matching. Okay? So, okay, practice. Which one is IFN and which one is not? And then how do you make it into IFN? So what do you think? A, is it IFN or not?
No.
No. Okay. So how do you make it into IFN?
Use cloud.
Correct. You add one cloud node here. So my question to you now, what is the flow in the cloud node? In this A. What is the flow in the cloud node in this A?
Is it the 1.5 plus
No.
1.5?
Yeah, plus. Right. So the cloud node here must have exactly the same as the sum of all flow out. Okay. And that also the same as the total of one flow in. Right? How about B? Is it strongly connected or not?
No.
No. Is it IFN? Of course not, right? So how do you make it into IFN? Again, you add cloud node. My question to you, what is the Z value?
2.
2. Very good. How about C? This one. Is this already IFN?
Yes.
Yes. Okay. In fact, if you look at this in the Markov chain, okay, this is cyclical irreducible. I hope you still remember. Leafy hate this. Right? It's a cyclical. Every three step come back to the same node. Right. So, how about this one? D. Is it IFN?
No, because there is a sync.
Okay, so you need to add the cloud node. So again, next question is, what will be the flow in the cloud node?
2.
2. Very good. Okay. How about E? Is it IFN or not?
Yes.
Yes. Yeah. You can check. Okay. So the sum of each is already balanced. So 4. This is 2, 2. 2. This is 2 and 1. So become 3. Right. 3 and 2 now become 5. So each you check, yeah, in each node they are balanced or not. Yeah? If in each node they are balanced, so this is IFN. Yeah? And this is irreducible. How about this one? F. Is this IFN or not?
Yes.
Yes. Okay, very good. So, okay. So now the next important characteristic of IFN that we can use for application is because IFN itself is a relative flow. Yeah? In its link, the flow is a relative flow. Okay? Relative means it is a rational number. Yeah? So originally it comes from random walk on network. So if you do a random walk on network, okay, and you take the flow in its length divided by the minimum flow or the maximum flow, practically divided by the statistic of the flow, okay, you will get asymptotic value, what is called ideal flow. And that's by definition. Okay. Now, because ideal flow is relative flow you understand, yeah? Flow divided by flow. Right? Flow divided by statistic of the flow, which is maximum, minimum, or the total. Yeah, so relative flow. So because it's relative flow, then it is scalable for the entire network. Yeah, that means I can say I have a new F here. Okay, I can scale with any value alpha. Alpha is positive real number. Okay, so yeah, so this I can also create, so this is not basis, this is supposed to be cardinal. Yeah, the cardinal network is the IFN with the minimum integer. So because this is rational number, right, then all the flow must have certain denominator, isn't it? Okay, so in that case, you can multiply with the LCM, the least common multiple of denominator, so that you can get integer. Yeah? So let's define equivalent IFN. So 2 IFN. So I have 2 IFN, okay, whose links flow in one network is a positive scaling of the other network. This is called equivalent IFN. Okay, so you just multiply with one number, global scaling. Okay, so again, this is not basis, this is supposed to be cardinal. Okay, so now interesting things in equivalent KFN. Okay, they have invariant stochastic matrix, they have invariance coefficient of variation of the flow, and then they have invariance average node entropy. So say you have 4 standard form of IFN. See, if the total flow of the IFN is 1, okay, we call this basis network. Okay. You can also divide by the minimum link flow, then you have minimum flow is 1, or you divide by the maximum flow, it's linked by the maximum flow, then you get the maximum flow is 1, right? But if you divide by the least common multiple of the denominator of all flow, you will get the cardinal network, which is the link flow of all integer with its minimum. Let me give an example. Yeah? So, say this is my flow. Okay. Right. So, this is my flow. Okay. And this is the cardinal. This is already in cardinal network, which is the minimum integer. Yeah, the minimum integer of the flow. So in that case, I can scale. Yeah? For example, because I want to get the flow of the total flow will be 17,500. How do I get that? Easy. Yeah? I want to get that. So what I will do, I need to get the scaling, right? How to get the scaling? The total flow here that I want, okay, divided by the total flow of this cardinal network, okay, and then I multiply all of this flow by that scaling. Okay, I will give you example. Okay, so this is the basis network. Yeah? Basis network means the sum, yeah, the total sum is 1. Yeah? Why this is basis? Because this represents the probability, yeah, of its link. Yeah? And because this is ideal flow, you will see the sum of this is all the same. Yeah? 16 over 49, 3 over 49. Yeah? This is pretty much equal. Right? Okay. Now look at the denominator of the numbers here. What is the denominator of the positive number? Denominator.
49.
49. Okay. So in that case, I multiply everything with 49. I will get the cardinal network. So that the total here will be 49. Clear? Okay. What is cardinal network? It's ideal flow. Okay. We scale it in such a way so that this is the minimum integer. Okay. The minimum is 1. You see, the minimum in here is 3, right? Okay. The 0 you ignore. Huh? I mean, the positive value, the minimum of the positive value must be integer. Yeah. Oh, how about this? Okay. Assuming this have cloud node, okay, can we get the coordinate network of this? What is the denominator? What is the denominator of this flow? 1.5 is 3 over 2. 2.5 is 5 over 2. So the denominator is 2.
Oh,
Correct? Right? This one, 2 is 2
4
over
over
1. 2
Oh,
over
yeah.
1, right? So now the LCM of 1 and 2 is 2. Right? So in that case, you multiply everything by 2, right? Then you will get this. Clear? Okay. So this is how you will get integer number of the flow. Next. Okay. Which one is the basis network? This one, right? The sum is 1. Okay. Which one is the cardinal network? This one, right? Okay. This is the minimum is 1. How about this one? This is all, the 4 of them are equivalent IFN. Okay. Okay. You just multiply this by 2. Yeah. From the cardinal network, you multiply by 2, you will get this. From the cardinal network, you multiply by 3, you will get this. Right? And then from the cardinal network, you divide by the total flow, which is 18, you will get the basis network. So they are all equivalent. Do you understand the meaning of equivalent network? Equivalent IFN. Okay. You just multiply by one scale factor. You see? Oh. Can you identify the cardinal network and find the scaling? This is all equivalent IFN. Which one is the cardinal network?
Upper left.
Upper left, correct. And then what is the scaling of this from the cardinal network?
Divide by 3.
Yes, so the scaling is 1/3. Multiply by 1/3, you get this. How about this one?
Half
Okay, half. And then how about this one?
times 500.
Very good. So easy, right? Super. Right. So now, if you have equivalent IFN, okay, why they are equivalent? Because they actually have the same, exactly the same stochastic matrix. Okay, equivalent IFN always have the same stochastic matrix. So the Markov chain is exactly the same. Okay, so you just scale it up or down so that you can get different flow. Okay, and other properties is now if you calculate the flow, okay, the mean of the flow and the standard deviation of the flow, positive value, that is called coefficient variation. Okay, all also the same. Yeah? And then if you calculate the entropy, the node entropy, all also the same. So this is the example. Okay, you can see this is the global scaling of this network. This is the average flow. This is the standard deviation of the flow. Okay, and if you divide, okay, you will get coefficient of variation of the flow. Okay, all of these have exactly the same coefficient of variation of the flow. And this is one of the characteristic of equivalent IFN. Okay. Okay. Now let's go to the detail. Okay, so that we can apply this. Okay. Say I have a very simple, this is not even a network. Yeah? If I have a node I and I have node J, right? Vi here is the value of node I. Okay, the flow in node I, which is the sum of all other flow in, okay, which is the sum of, the same as the sum of all other flow out. Okay, so what is the meaning of this node value? Okay, the node value, okay, that is the same as the sum of the flow in each column or the sum of flow in each row, right? Now, if you get that divided by the total flow, you get the probability of each column and probability of each row. Do you get what I'm talking or you don't? Okay, let me give examples so that you can get better. Where is the sample? Yeah. Say you have a data table. Here, this is the table. Okay. Can I just put this data table? This is variable A, this is variable B, this is variable C. And then this is the value. Okay. Each row is A1, A2, A3, and so on. From this data table, can you calculate the crosstab? Do you get the crosstab or not? Do you understand the meaning of crosstab, cross tabulation? So here, yeah, I will give you A1 and B1. How many it happened? How many times it happened? A1 and B1 in this table. A1 and B1, one.
Only one.
Only one. Okay. How about A1 and B2? How many times it happened?
A1, B2
This one,
times.
and this one. 3 times. Correct?
Yeah.
Okay. So A2 and B1. A2 and B1. This one A2 and B1. This is A2.
Times.
So 3 times. Can you get it? So cross tab represent the frequency. Okay. How many times it happened? Is it clear or not? The meaning of cross tab. So you have a table, yeah. Okay, and then from that, okay, you get the frequency. Okay, so I can also get the from A and C, B and C, right? Is this okay with you, cross tab? Now suppose I have this cross tab. Okay, so I have X and Y. Okay, I have X and Y. This cross tab, from the data table, you can create cross tab, right? So now suppose you already have the cross tab. Okay, so if you sum to the row and you sum to the column, okay, this is, let's call this sum VA, VB, yeah, VC, VD, and VE. Yeah? And then this is the kappa. What I'm talking about? This is every cross tab that you make is actually flow. Okay, and then how I will get the stochastic matrix? Easy. Yeah? Every number here I divide by the sum of the row, right? So 2 divided by 10, 1/5. Yeah? And then 3 divided by 10, it is 3/10. 5 divided by 10, 1/2, correct? Yeah? So you get the stochastic matrix. Okay. And how about this? This is, so stochastic matrix is basically percentage by row. Right? How about this one? T here represent the percentage by column. And you see? Now 2 divided by 8, yeah, 6 divided by 8. This one. Yeah? 3 divided by 12, 9 divided by 12. So you get this value. Okay, so that the total sum of the probability is 1. So this is percentage by column. In statistics, did you study this? Percentage by row, percentage by column.
I don't know. I don't think so. Or maybe I forgot. But I don't think so. Not that I recall.
Okay, okay. So then this is new. It's okay. Okay. So now you get the percentage by row. This is percentage by column. Now I want to get also percentage by total. How do you get percentage by total? This 2 divided by 35. Okay. This 3 divided by the total. It is 35. Okay? Can you see this? Now, if I sum all of this, okay, I got this probability 2/7, 5/7. Yeah? If I sum in here, I get this is called marginal probability. Okay, this is called link probability. Okay, or sometimes we call this joint probability. I hope you studied joint probability in statistics, no? Probability of intersection between X and Y, right? Okay, my next question, did you study this notation, conditional probability? Yes. So, do you know that this one, yeah, the stochastic matrix is actually conditional probability? Okay, the same thing with this. Yeah? This is also conditional probability. Right? So percentage by column, okay, this is actually conditional probability. Given C, okay, given C, what is probability that this is come from A? So this is probability of A given C, 1/4. Okay. This one, 3/4 is probability of B given C. Okay. How about this one? 1/5 in here. Probability of what? C given A. Is this confusing to you or? I just want to tell you that basically percentage by row in IFN, this is the same as outflow probability. Percentage by column is the same as inflow probability. And you know Bayes theorem, right? Bayes rule. Okay. So because of the Bayes rule, so you practically can connect. Okay. Say this is the IFN. Okay. And you know the inflow probability and outflow probability. You can actually get the node value. You can also get the inflow or outflow probability out of this IFN. Okay. Now suppose you have the table a while ago, right? So you have the table like this, and then you can calculate the crosstab. Okay, based on this crosstab, you can also get the say this is the crosstab of A and B, right? Then you can get the IFN out of this crosstab. Okay, simply by adding Z. So this is the actual crosstab that you have here, 1331, right? This is the initially 1331 here, and if you put it there 1331 here, now you add Z, okay, you get IFN. So what does it mean? Okay, it means every crosstab, every data table that you have, okay, you can create IFN, and this IFN actually reveal the hidden structure behind your crosstab. Okay, there is some kind of hidden structure behind your crosstab that is not revealed unless you create IFN. So this is interesting, right? Because now you can reveal something behind the scene. Okay, and from there you can calculate the joint probability and so on, right? And you can also combine. Okay, so let's do another application of IFN so that you can get to understand. Suppose you want to apply IFN, right? What you will do? That's the question, right? Okay. So IFNs come from a traffic flow network as modeling metaphor, right? So I use name flow, congestion, premagic, yeah, irreducible, and so on. These are the term, the jargon, isn't it? Right? So now, if you want to apply this, okay, as long as your problem can be formulated as flow equilibrium in a strongly connected network, okay, then you can start to consider, oh, if I have this problem, I will use IFN. Okay, what is the requirement? Flow equilibrium in a strongly connected network. Then you say, when I will get that? Okay, right? So, well, look, you think in terms of structure, network structure and network utilization. You are the one who decide, okay, what is the meaning of this node? What is the meaning of this link? What is the meaning of trajectory, the sequence of node? Okay, and then if your network is actually not irreducible, right, not strongly connected, then you can add cloud node to make it strongly connected, isn't it? Right? So, and then you can transform that data into some kind of capacity matrix, okay, say by reading trajectory. Yeah? After that, you compute the ideal flow using that formula a while ago. Then you can get Markov transition matrix, right? And then based on that, you can apply the IFN. Okay, so depending on you how you will apply, okay, all you need to do is think of the interpretation that you want. Okay, what is the meaning of this network structure? Yeah? Okay, and then how you will read the trajectory. What is the meaning of your flow? What is the meaning of link and flow and trajectory? Okay, so let me give example. So in transportation, right? So the node represent the intersection. The link represent the road segment, right? The flow represent the count of vehicles in that link or in that intersection, right? So, and then from there you can calculate the congestion, the speed, travel time, delay, and so on. Okay, now you are saying, okay, I want to apply this in decision analysis. Of course, now node represent the alternative, right? The state of nature, the payoff, right? And the link represent the possible possibilities. Yeah? The flow represent the information. And probably you want to calculate the minimum payoff. And so on, right? Say, you want to apply this to natural language processing, AI. Right? What you will do? Oh, one way to do, okay, the node represent each word. Okay, what is the link? The link represent the bigram or trigram. That means connection between two words or connection between three words, and so on. So how many words that you want to connect together? So the flow represents the co-occurrence. That two words happen together. Okay, so. And then you check, for example, this performance is, oh, this is the word of somebody. Yeah? For example, it is your writing, so I can check that this is your writing based on the appearance of how many times you always use commonly those kind of words. Right? So for example, I want to check whether this is the letter from St. Paul or this is the letter from St. Peter. Right? So Peter and Paul use different word, right? So then I can check this big diagram and how many times it occurred. And then from there, I can guess personal characteristic of that word. Okay. Say, you are talking about time series analysis. Last time we in Markov chain, yeah? So then you talk about the position, right? So what is the value of the price? Okay. And then the link probably the return value, yeah? The change of the price, right? And then the flow represent the probability, how many times it happened, occurred. And then the performance, of course, when are you going to buy stock, for example, when are you going to sell the stock and how much your profit and so on. So the same thing, yeah, we can apply to many other application here. Yeah? For example, color, yeah, you want to create the image, right? So that means every node represent pixel, right? And then this is now depending on your neighbor, yeah, neighboring pixel, right? And then you are talking about neighboring probability of occurrence between the neighbor of that pixel, right? So, and eventually you will get the image characteristic. Yeah, the same thing with music, right? Music is easy. Yeah, you get the musical note, right? So that means every musical note is one state. Yeah, the note in IFN. Yeah. In medicine, the same thing. Yeah, every note represents the sickness or the symptom. Yeah, or represent some health problems or some medicine probably. Yeah, and then the link represents the amount of severity and so on. So how do you get the trajectory? You get it from the story from the patient. So again, last time I show you the application of IFN in many different contexts, isn't it? Text processing, table, right? Even image processing. Yeah. Again, all we need to do is just to interpret, yeah, the meaning of node, the meaning of links, and the meaning of flow. Okay, up to here, is there any question? Clear, yeah? I hope. Okay, so yeah, so in industrial engineering, for example, you want to do a facility layout, okay, where I will put my machine, for example. So that machine represent the node. Okay, and then the space between the machine represent the link. The route or the road between the machine represent the links and so on. Okay. So let me give you the last example here. The last example here. Oh, in transportation, yeah, before the last. In transportation, okay. Okay, I can apply this in IFN. Okay, I can do it in transportation network, example. What is that for, right? You are asking, what is that for? Isn't that the question, right? So then you can simulate, okay? So you can simulate, what if I add lane? Okay, how if I reduce the lane? What's the meaning of adding lane? Okay, whether it's temporary or permanent. For example, you don't allow parking anymore. Okay? When you don't allow parking, that means what? You add additional lane, isn't it? Right? Or maybe you want additional lane real for permanently. Okay? Additional lane is adding. So you expand the road. Possible, right? You expand the road. Yeah? And reduce the lane. For example, temporarily, yeah? So there is some VIP will pass by that time, for example, or that road will become bazaar or market. Maybe there is some protest or demonstration, maybe some festival or religious event. So temporarily that lane or that link will be remove, right? So then you can check what is the effect of that removal. What is the effect of that additional? Okay, say you add some width to the road, okay, or you reduce the width. For example, you want to plant the trees along okay, certain road, whether this is actually better, beneficial or not. So you can check the scenarios that you have. Yeah, the same thing. Yeah, so you can say, what will happen if I reverse the direction of the road? What if I make it one way? Say usually two ways. Suddenly you make it one way. That means the lane capacity increase, isn't it? The same width before two ways now become one way, right? So does it actually make the road better? Will it actually reduce congestion or not? So I give you an example here, very simple. In this example, I want to see the effect of adding one link. Okay, very simple example. This is all numbers are ideal flow, so 1, 1, 1, right? Okay, and let's assume they are equal probability value. Okay, so if I have 2 in here, you divide by 2, 1, 1. So say from this road network, I add one more link, yeah, this red. So you see here, when I add one more link, assuming they are the same capacity, okay, that means when I add one more link, these two roads are getting more congested. Can you see that? From here, I add one more link here. Okay, what happened? If I add one more link here, this road will become 4 times more congested, or 2 times more congested than this. So you can check immediately the effect of adding more road. Hey, you may say, hey, adding more road actually increase the congestion level. Yeah? Is it always like that? Let us check. Okay, so I add from here, I add one more link here. Okay, okay, and then we calculate the ideal flow network. You see, from 4 maximum congestion 4 now becomes 6, isn't it? Okay, so yes, it increased. It increased the adding link, increase the flow because the capacity is the same. So in that case, the congestion level is increased so much. But is it always the case? Okay, from here I will show you two scenario. Okay, so if I add this link, okay, from here I add this link. Okay, so you can see the maximum congestion here 3.5 and this is 4. So from 6 actually reduce, from 6 to reduce to 4 and to 3.5. Okay, so you can see that no, adding link not necessarily increase congestion, yeah, depending where you add the link, right? And in fact, you can optimize, right? Meaning the certain link that you add actually will beneficial compared to this one. Yeah, this is 3.5, this is 4, right? So you can start to compare the scenario of the chains. Can you get it or not? Say you have a system and then you change something. Okay? Before you change, this is the situation. After you change, that is the situation. Then now you start to compare. Is this something useful? Right. So say in this scenario, okay, this is the simple node network. I want to see the greatest reduction of maximum flow. Okay, so if you see here, the maximum flow is link AB, right? So now I want to add, okay, the policy is I want to add one link to the network, which will greatest mean maximum reduction, delta maximum flow. So you can simulate Okay, and you can calculate, oh, this is actually, if you add this link, will reduce congestion, okay, from 22% to 16%, and so on. So you can simulate. Okay, so not only that, this is the interesting part here. Usually, what you simulate, you can only predict maybe value, right? But in here, I can show you, we can predict also the when and where, space and time. Wow, right? So for that purpose, we need to add additional model. Yeah. So I got the total flow here. It depends on population and the number of car. Okay, and this is the assumption of this model. So say the city population is this much at this year 2000, the car population is this much, and then say per lane we assume 1,500 vehicles per hour, and assume the growth rate of the population and the car growth rate, yeah, 7%. So with this assumption and the model, we can predict where and when the traffic congestion will happen under certain policy scenario. So let's assume so this is the base case, year 2000. Okay, this is the capacity, and this is the vehicle per hour. Okay, and you get the total flow in the network is 10,000 something. Okay, and what happened is you check the maximum congestion. Yeah, you get the maximum congestion. In this case, link DC. Okay, oh, where is DC? There, here. The maximum congestion happened 0.61%, okay, in link DC, right? And then I want to determine, okay, 0.6 is not congested. Okay, in traffic, we say traffic is congested if your congestion level is actually 0.8 or 0.9. So let's assume 0.9. Then when will happen to have 0.9? Yeah, because we can get the scaling factor. Then we can list it the number of population, the number of car, and from there you can calculate the total flow, right? This will happen in the year of 2009. So 9 years later, okay, it will reach that congestion level. So I can get the time. And then I will also get where with this link. What is that? Link DC. Okay. And then say at that time in 2009, because this is congested, link DC is added one more lane. Okay? Because it's congested already, right? So the policy said, look, if 0.9, let's add one more lane there so that reduce. Okay, what will happen? Okay, so this is already 0.9. We reduce the congestion in this lane only, with this link only, by adding one more lane in this link that is the most congested. Right? Usually that's what the government do, right? Oh, this is congested. Okay, I will add one more lane, yeah? Pelebaran jalan, right? Correct? In Jakarta, it's very common. Right? Yeah. So they remove the housing, they add one more lane. Now the road become bigger, isn't it? Wider. Right. Okay. So then what will happen? Okay. So when you add one more lane in this link, DC, okay, suddenly the congestion level becomes 0.6. Oh, no more congestion. Happy, right? Okay. So forget. Look, if you use IFN, what you will do, you can actually see that the congestion is actually shifted, not from link DC, it will go to link BC and DE. So using this, you can see the effect in the entire network. Right? Yes, you improve here, but you are actually making worse in the other side. Unknowingly. You can simulate this because you start to. This is a very good tool, isn't it? Right? Because you can see the effect, okay, in the whole system rather than just that link. Right? So you can see, oh, I improve here, okay, but actually it will make worse in other side. Okay. Yes, this is worse, 0.8, okay, congested in other side, but not yet 0.9. Okay, when is that 0.9? You compute again, right, using the scaling. 0.9 will happen, will the total flow like this happened in 2010 because of the model that we had earlier. Okay, so we also know not only the space which is where which link, we also know the time when that congestion will happen. Okay, and then we can continue the same manner. Yeah, you see, okay, in different years, this will reach threshold of 0.9. Okay, and which link we know also, and what is the maximum congestion after adding one more lane. Yeah? And so on. So this is interesting, right? Because now you can see, I can predict which year and which link where, okay, the traffic congestion will happen based on certain policy that you want to add one more lane when the most congested in the most congested link. Yeah. So I don't know. Is this something useful? Right. So now I want to debunk the myth. Okay, okay. The government always say, "Look, I want to add one more lane. Okay, let's widen the road." Right? So, is it actually widen the road always improve congestion? Yes or no? Yeah. So I said this is actually myth. Okay? Adding lane will improve congestion in the network. That is actually myth. Yeah. Improving the congestion in a link, yeah, might worsen the congestion in other link in the network. Yeah? So, so I want to prove, yeah, how to prove that? Simple, yeah. I just reduce the number of lane, reduce, not increase, yeah. I reduce the number of lane, and then I can improve the congestion. Okay, so say in this example, this is the capacity, this is the number of lanes. Okay, you can see there is 5 lanes in link AC here. Okay, and these are the assumption that we make short term. Okay, and this is the congestion level, maximum congestion is 0.85, right? And then what happened if instead of 5 lanes, okay, the same network, exactly everything the same except this link, I reduce from 5 lane to 2 lanes. Okay, and you will see it's actually reduced the maximum congestion level. And this is, look, in South Korea, in Seoul, okay, they do that. Okay, so there are certain road that is congested, and then they remove that road and then they make it into garden and actually make it better. Right? So this is just a tool to prove that mathematically. Okay, so it's a myth that increasing the number of lanes will improve congestion level. Okay? And you probably don't feel the pain. Yeah? If you have your house, your own house, actually demolished because of the road widening, what you will feel. Right. So that's based on the myth. Right? So that even worse, right? Because of the myth that actually improve congestion level, which is actually not. Okay. Then you need to sacrifice your own house. So, okay. So this is the example of the application of ideal flow network that you can see. Yeah? Of course, there are many other examples here that you can check on your own. Okay, the last one that I want to show, this is already clear. Okay, this is in agriculture. Okay, so ecology. Yeah? So human produce garbage, right? And then the garbage will be eaten by the worm. Okay, the worm will be given to the fish, right? And then the fish will produce feces of the fish or the will produce some nutrient to the plant. Yeah? And then the fish and the plant will be eaten by the human. So assume only one human, then you can actually compute. Yeah? Look, the flow here have different meaning. Can you see this? This is functional. This is a strongly connected network. Okay, but the meaning of premagic here, meaning equal, equilibrium. Yeah. So based on this assumption, you can read on your own. Yeah, we can calculate. Okay, for one human, can they survive? One human. Okay, how many species you need? How many plants do you need? How many worms do you need? Okay, so that that human will survive. Everyone will survive in that ecology. So you can calculate. Okay. And what is the time? Okay. Then you can calculate. This is the example of computation using a very simple IFN. Okay, you can think. Yeah. So one human need to produce 90 kilogram fish meat in half year, right? Okay. So they need 45 fish. Okay. They need 18 kilogram of plants. That means okay, they need to plant how many times and so on. So meaning it is, the question is actually in this simulation is it possible for a human to survive alone in that environment together with the fish and plant? So of course this is just hypothetical. Okay, the answer is yes, it's possible. Right. So yeah, this is just the computation of the detail. Yeah. So my point is, look, the FN, the flow, not necessarily the same unit. As long as you can find the conversion factor in its node, you can create IFN. So with this, I hope this is useful for you. I don't know. Give me feedback.
Sir, actually, I want to ask,
Yes.
like, how can we know if a problem can be solved by IFN?
Yeah, two things. IFN is irreducible,
Mhm.
right?
Yeah.
Reducible means strongly connected. So if your problem can be put into strongly connected network,
Mhm.
we
Okay.
use as FN. Yeah? The next one is whether you can have a balance. Okay, balance means equilibrium. Okay? So that's why in the beginning I defined that. Yeah, what is the meaning of irreducible? What is the meaning of premagic? Correct. Once you can define the meaning of, so in the beginning of the slide of IFN, okay, I give you irreducible interpretation, unity, right, whole, only connected, and premagic mean balance, equilibrium, give and takes, right?
So as long as the problem is strongly connected, it can
Correct.
be
Strongly connected
solved.
and equilibrium. Yes, you can.
Okay.
Okay. So that's the only requirement there. And you know, if not strongly connected, you can add one more cloud node. You can make it strongly connected.
Okay.
Okay. So with that, you can apply. Don't forget, yeah, IFN is basically Markov chain. Okay, when there is a long-term view or steady state condition. So,
Mm.
in fact, this is like irreducible, yeah? Regular Markov chains. By doing IFN is you are basically backed by the theory of Markov chains, yeah, and the maximum entropy. Okay. So thank you for the semester. I hope this is useful for you. Okay. And yeah, that's it. So see you on Friday for your presentation.
Okay. Thank you,
Okay.
sir. See you.
Joy, are you going to meet again with
Pardon, sir.
Matthew later?
Matthew.